Imagine a star so large that the Sun is no longer the object in the picture. It is only the scale marker. A bright dot beside a red atmosphere so wide that if it sat where our Sun sits, the familiar inner solar system would disappear inside the comparison. That is the kind of image that makes the question feel simple. What is the biggest star in the universe? But the honest answer begins with a stranger question. Where does a star end? A planet has a surface, a rock has an edge, a star has layers of gas, light, heat, opacity, turbulence and dust, fading outward until the word edge starts to become a measurement rather than a place. That fading edge turns a familiar record question into an investigation. By the end of this video, you will understand why the most honest answer starts with a boundary rather than a trophy. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. The biggest star question survives because it gives the mind something solid to hold in a universe that is usually too large to picture. Most cosmic numbers are abstract. A light year is already beyond ordinary experience. A galaxy is a word we learn before we can really imagine it. But a star larger than the orbit of a planet feels different. It turns scale into a scene. You can place the Sun beside it. You can imagine Earth reduced to something invisible. You can watch a graphic step from a normal star to a giant, from a giant to a supergiant, and feel each jump as a physical humiliation of human scale. That is why the question attracts such confident answers. One chart says UI Scuti, another says Stephenson 218, another points to WOH G64 or VY Canis Majoris, or a candidate with a designation that looks less like a name and more like a catalogue accident. The public version of the topic encourages a trophy cabinet. Here is the largest, here is the winner, here is the red sphere that beats all the others. But when the question enters actual astronomy, the trophy begins to wobble. The issue is not that astronomers are being evasive. It is that the word biggest is carrying too many meanings at once. A child can ask the question in one sentence. A careful answer has to ask what kind of size is being counted. Radius, volume, mass, brightness, apparent size in the sky, temporary expansion during an outburst. Even after we choose radius, the answer depends on how that radius was measured. Was the star resolved directly or inferred from light and temperature? How certain is the distance? How much dust is between us and the star? Is the star changing brightness while we measure it? Is the object even a clean single star, or part of a crowded, dusty region where membership and identity are not trivial? The most important shift is this. The biggest star is not like the tallest mountain. Everest has a summit. It can be argued over at the level of snow depth or sea level reference. But the mountain has a surface. A red supergiant does not present a hard wall to space. It presents an atmosphere. It presents a photosphere, the layer from which light can escape. In the most extreme evolved stars, that layer is wrapped in motion, dust and low-density gas. The outer parts are not a clean shell. They are an event happening over time. That does not make the question meaningless. It makes it better. A fake answer would be easy. Choose the largest number from a list and declare a champion. The stronger answer is more cinematic and more truthful. It shows why giant stars are so difficult to rank, why famous names rise and fall in public charts, and why the real boundary of the question is not just between one star and another, but between an object and the method used to measure it. The danger with a subject like this is that the image can outrun the evidence. A red sphere drawn across the orbit of Jupiter is powerful, but the graphic does not tell you whether the radius came from a direct angular measurement, an inferred luminosity, an assumed distance, or an older public value copied from one list to another. The number can look equally precise in all cases. The method is where the truth lives. Every famous candidate is therefore a scene in a larger investigation. Scuti is the scene about old public certainty. Stephenson 218 is the scene about the tempting modern champion. WOH G64 is the scene about record churn and modelling. Antares is the scene about measuring a real red supergiant atmosphere. Together, they build an answer that is more durable than any one leaderboard. The useful discipline is to keep returning to the quiet question of measurement. A dramatic radius is not rejected simply because it is dramatic, and a famous candidate is not accepted simply because the name is familiar. The evidence has to carry the weight of the image. That is the difference between wonder and spectacle. Wonder can survive careful measurement. Spectacle usually needs the caveats removed. The reason this matters is that record language creates a false sense of closure. Once a name is presented as the answer, the mind stops asking how the answer was produced. But the largest star is not a number sitting alone in space. It is a conclusion built from observations, assumptions, and definitions. If any of those pieces changes, the conclusion can move, while the star itself remains exactly where it was. So the strongest version of the question does not ask for a trophy first. It asks for a method first. What property is being ranked? Radius. What boundary is being counted? The light escaping surface, not a hard shell. How was that boundary found? Sometimes through direct angular measurements, often through inference. Those questions turn a familiar space fact into an investigation. The names still matter, because names make the mystery concrete. Scuti, Stephenson 218, WOH G64, VY Canis Majoris, Antares, and Betelgeuse each reveal a different part of the problem. One teaches public memory. One teaches distance and membership. One teaches model dependence. One teaches dust and mass loss. One teaches atmospheric measurement. One teaches variability. By treating the candidates as evidence rather than contestants, the answer becomes sturdier. The largest star question can still deliver the scale people came for, but it also delivers a better instinct. Never trust a cosmic ranking until the ranking tells you what it measured and what could move it. The public question also has a social life. It travels through posters, school graphics, shorts, documentaries, and search snippets. Each retelling tends to keep the most dramatic number and lose the uncertainty attached to it. That is why a largest star claim can feel settled in public long after the specialist literature has become more cautious. The myth is not invented from nothing. It is usually a real estimate stripped of its conditions. A better opening habit is to treat every record as a claim with a history. Who measured it? In what wavelength? What distance did they assume? Was the object variable? Was the star inside a crowded field, or an association whose membership matters? Those questions do not make the subject colder. They make the scale more durable because they show why one number deserves more trust than another. That is why the candidate names should appear as milestones rather than rankings. Scuti shows how public certainty can age. Stephenson 218 shows how a tempting modern claim depends on distance and membership. WOH G64 shows how new candidates can enter through modelling and extragalactic context. Antares, Betelgeuse, and VY Canis Majoris show the physical behaviour behind the measurement problem. The public answer often travels faster than the evidence attached to it. A striking comparison graphic can detach from its source, then reappear for years as if the number were a permanent fact. That is why an honest answer has to begin with method rather than a crown. The claim is not only the star's name, it is the distance, the boundary, the temperature, the dust correction, and the confidence carried by each assumption. A red supergiant makes this problem unusually vivid because its size feels visual before it feels technical. The sun can be drawn as a small marker beside a swollen red atmosphere, and the comparison immediately communicates scale. But the smooth circle in the graphic is a translation. It compresses a turbulent gaseous boundary into an edge the eye can understand. The better question is not meant to reduce the scale. It protects the scale from becoming a loose myth. If a star is described as 1,000 solar radii, the phrase should bring evidence with it. How was that radius obtained? Was the star directly resolved, or was the value inferred? How much could the answer move if the distance changes? A strong answer keeps those questions alive. The named candidates are therefore best treated as clues. Scuti explains old public certainty. Stephenson 2 Asmat 18 explains the temptation of an extreme modern claim. WOH G64 explains how new observations can reshape the field. Canis Majoris, Antares, and Betelgeuse explain atmosphere, mass loss, and variability. Together they turn a simple search query into a real investigation. The first discipline is to separate wonder from certainty. Wonder can begin with a picture, a red atmosphere swollen beyond any ordinary human scale, a sun reduced to a small comparison point, a solar system made fragile by perspective. Certainty requires a different toolset. It asks whether the radius came from a direct angular estimate or from luminosity and temperature, whether the distance is robust, and whether the object is being observed through dust. Holding those two modes together keeps the story from becoming either dry or careless. Public memory also has inertia. Once a name is attached to the phrase largest star, it tends to remain there long after the underlying estimate has become less secure. Search results, posters, classroom graphics, and short videos can preserve an answer as a cultural fossil. The useful response is not mockery, it is reconstruction. Follow the claim backward until the assumptions appear. Then decide how much weight the name can still carry. The central question therefore becomes a test of intellectual honesty. A simple answer gives comfort because it closes the loop quickly. A measured answer gives something better because it explains why the loop was difficult to close. The largest star is not merely a piece of trivia, it is a demonstration of how astronomy turns distant light, uncertain distance, and turbulent gas into a number that can be compared. A useful comparison begins with the Sun but does not end there. The Sun is already so large that Earth becomes a speck beside it. Yet the largest red supergiants make even that familiar star look modest. This inversion creates the emotional pull of the subject. The caution is that the comparison line marks a light-defined atmospheric radius, not a solid wall in space, and that difference has to remain attached to the image. The question also reveals how astronomy handles language borrowed from everyday life. Words such as big, edge, surface, and diameter sound simple because they work well for rocks and planets. Applied to a swollen star, they become technical shortcuts. Each shortcut is still useful, but only if the hidden definition is remembered. The largest star search is partly a search for the right translation between human words and stellar physics. Another useful way to begin is with humility about maps. Every comparison image is a map of a physical claim, and maps always choose what to show. They can show radius against planetary orbits, but they cannot show every uncertainty in distance, extinction, temperature, or atmospheric structure. The image is not false because it simplifies. It becomes false only when the simplification is mistaken for the whole truth. The largest star question deserves an image, but it also deserves the conditions behind the image. The question also benefits from resisting false precision. A number with many digits can sound more trustworthy than a rounded estimate, even when the underlying uncertainty is large. For extreme stellar radii, honest rounding often communicates more truth than impressive specificity. The point is not to drain the number of drama, it is to make sure the drama comes from scale rather than from a misleading appearance of exactness. The first answer most people expect is radius. In everyday language, the biggest star is the one with the greatest distance from its center to its visible edge. Radius is intuitive because it turns into comparison graphics. Put the Sun beside a red supergiant and the story is immediate. 1,000 solar radii sounds enormous because it is enormous. A star with a radius 1,000 times the Sun does not merely look 1,000 times wider. Its volume, if treated as a simple sphere, is roughly 1 billion times the Sun's volume. That is the kind of number that makes the mind reach for images instead of arithmetic. Volume adds drama, but can also mislead. If radius increases by a factor of 1,000, the mathematical volume increases by a factor of about 1 billion. That sounds like a final answer, but in a red supergiant, the outer envelope is incredibly diffuse. The volume being counted is not a solid container packed with star material. It is a vast region of gas whose density falls outward. The emotional scale is real. The physical interpretation needs care. Angular size is different again. A star can look large in the sky because it is nearby, not because it is physically the largest. Some giant stars can be measured more directly because their apparent disks are large enough for interferometry. That makes them wonderful teaching examples. It does not automatically make them record holders. Distance is doing part of the work in how large they appear from Earth. Then there are temporary sizes. Some objects expand dramatically during eruptions or transient events. Their apparent radiating surfaces can become enormous for a time. Those events matter, but they are not the same question as the largest known stable star by radius. If a star-like event swells outward during an eruption, it may create a spectacular photosphere, but a temporary outburst is not a permanent crown. For our purposes, the central question will mostly mean largest estimated radius among known stars or star candidates. That is the version people usually want, but we will keep the other meanings visible because they are the source of most bad answers. Biggest by radius is not biggest by mass. Biggest by mass is not brightest. Brightest is not widest. Widest on the sky is not necessarily widest in space, and an expanded transient is not the same as a settled giant. The word biggest has to be narrowed before it can be answered. The question can be simple while the answer stays careful. People arrive for the biggest star, and the story should answer that promise. But answering it well means refusing to slide between meanings whenever the drama needs a boost. If we mean radius, we should say radius. If we mention mass, we should make clear that mass is a different contest. If we mention luminosity, we should not let brightness masquerade as width. A good way to keep the distinction alive is to return to it whenever a candidate appears. What is being claimed here? Radius. How was it estimated? With what distance? With what temperature? Does the star have a dusty envelope? Is it variable? The repeated questions turn a list into an investigation. Radius is the best working definition for the public question because it corresponds to physical width. It is the measurement that makes the sun disappear beside a red supergiant. But even radius is a chosen definition. Another astronomer asking about mass would point toward a different population of stars. Another asking about luminosity would build a different list again. This difference explains why public conversations often feel contradictory. One source celebrates the largest by radius, another celebrates the most massive known star, a third emphasizes the brightest or most luminous object. All of them may be discussing extreme stars, but they are not answering the same question. The confusion begins when the word biggest is allowed to float between categories. The volume distinction is especially useful because it delivers awe and caution at the same time. A red supergiant can occupy an immense mathematical volume, yet its outer envelope can be thin enough that ordinary ideas of fullness fail. The scale is not fake. The mistake is imagining that the volume is filled like a planet or a metal sphere. Temporary expansion adds one more boundary. Astronomy includes eruptions, transients, and outbursts whose apparent radiating surfaces can become enormous. They belong to the wider story of stellar behavior, but they do not answer the stable largest radius question in the same way. A temporary glowing shell is not the same thing as a settled red supergiant photosphere. With the definitions separated, the rest of the answer becomes cleaner. The search is not for the heaviest star, the brightest star, the nearest large-looking star, or the most dramatic transient. It is for the largest estimated stellar radius among known candidates, with all the uncertainty that phrase honestly contains. A radius claim becomes most useful when the competing meanings have been cleared away. If the subject were mass, the story would move toward the most massive hot stars and very different physics. If the subject were luminosity, temperature would dominate the emotional picture. If the subject were angular size, nearby giants would matter in a way that has little to do with absolute diameter. Radius is only one lane, but it is the lane the public title is asking for. The mass distinction is especially important because it corrects a quiet intuition. People often imagine a bigger object must contain more material. Red supergiants break that intuition. Their outer layers can stretch outward to extraordinary distances while remaining tenuous. The star may be vast in radius without winning the mass contest. That makes the object stranger than a simple supersized sun. Luminosity creates a second false shortcut. Brightness has emotional authority. A star that outshines millions of suns sounds as if it should be the largest, but a hot compact star can radiate fiercely from a smaller surface. A cooler red supergiant needs much more area to produce high luminosity. The same light output can imply different sizes depending on temperature. Angular diameter supplies a useful observational twist. Some stars become easier to study not because they are the absolute largest, but because they are close enough and wide enough on the sky for instruments to resolve. These stars can be better teachers than more extreme candidates. In a documentary about measurement, a well-measured example can be more valuable than a poorly constrained record holder. Radius remains the most useful definition for this story because it matches the image people expect, physical width. Yet radius has to be separated from the other extremes. The most massive star belongs to a different contest. The most luminous star belongs to another. The widest object on the sky may simply be close enough for its apparent disk to be measured well. Mass is the easiest trap because everyday intuition links size with amount of material. Red supergiants break that habit. Their outer envelopes can be enormous while also being diffuse. A hot blue star can contain more mass inside a smaller diameter, while a red supergiant spreads its outer layers across a breathtaking volume. Bigger across does not mean heavier. Brightness creates a second trap. Luminosity depends on both temperature and surface area. A smaller, hotter star can radiate fiercely, while a larger, cooler star uses its huge area to produce immense total light. If brightness is allowed to impersonate size, the ranking becomes meaningless. The category has to stay fixed before the evidence can be compared. Temporary expansion also needs a boundary. A violent eruption can create an enormous apparent radiating surface for a time, but that is not the same as a stable stellar radius. The distinction matters because record language tends to flatten every spectacular event into one contest. A durable answer must specify whether it is discussing a star, a phase, or an outburst. A radius ranking has to stay loyal to radius even when other extremes are more dramatic. The most massive stars pull the imagination toward raw gravitational power. The most luminous stars pull it toward energy output. The hottest stars pull it toward temperature and color. Red supergiants win attention for a different reason: physical breadth. Their importance in this story comes from how far their light-emitting atmospheres extend from their centers. The distinction between width and mass changes the mental image. A red supergiant is not a scaled-up solid sun. Its outer envelope is loose, expanded, and low density compared with ordinary expectations of an object. The volume implied by the radius can be staggering, but the material near the outer layers is not packed like rock or metal. Width describes reach, not heaviness. The category discipline also prevents false arguments between sources. One source can name a massive blue star, another can name a red supergiant, and a third can discuss an eruptive object with a temporary photosphere. They may all be describing extremes, but they are not answering the same version of biggest. Once radius is chosen, the rest of the evidence can be judged on the right scale. A second reason radius matters is that it gives the cleanest link between physics and imagination. Mass can be invisible. Luminosity can overwhelm without showing width. Radius draws a boundary around the object and lets scale become spatial. That is why public interest gathers around radius even when other stellar records may be more fundamental to astrophysics. The radius definition also helps prevent a common exaggeration. Saying that a red supergiant would reach beyond the orbit of a planet can be meaningful, but it should not imply that the planet would encounter a surface like stone. It would be inside an extended stellar atmosphere, with conditions changing across a vast region. The mental picture stays powerful when the physical distinction is kept clear. The word stable also needs care. No red supergiant is perfectly stable in the everyday sense, because its outer layers can vary and shed material. Here the distinction is between an ordinary stellar radius estimate and a temporary radiating surface created by an eruption or transient event. That boundary keeps the subject from absorbing every spectacular expansion in the sky. A persistent evolved star and a temporary outburst can both be enormous, but they belong to different physical categories. There is one more useful distinction. Physical width and emotional size are not the same. A star can dominate the imagination because it is nearby, famous, bright, or culturally familiar, even if another object has the larger estimated radius. The investigation has to respect emotional familiarity without letting it choose the result. The answer belongs to the defined property, not to the name that feels largest in memory. Now the question becomes stranger. Even if we agree that biggest means radius, what radius are we measuring? With a planet, the answer feels ordinary. There is ground, ocean, cloud, atmosphere, and then space, but the solid body gives us something familiar. With a star, there is no surface in that everyday sense. You could not stand on the sun, you could not land on a red supergiant. The visible surface of a star is better understood as a photosphere, the layer from which light can escape outward freely enough to reach us. That sounds simple until the star becomes enormous and cool. In a compact star like the Sun, the photosphere is still not a solid surface, but it behaves sharply enough for everyday explanations. In a red supergiant, the atmosphere can be extended and turbulent. The outer gas can move in vast convective structures. Dust can form around the star. Different wavelengths of light can trace different layers. The edge becomes less like a wall and more like a fog bank at sunrise. There is a place where visibility changes, but not a hard line you could touch. This is why Antares is so useful as a teaching star. Antares is not being used here as the largest known star. It is being used because astronomers have studied its surface and atmosphere with interferometry. The European Southern Observatory describes Antares as a huge, cool red supergiant in a late stage of life, with a diameter about 700 times that of the Sun in its public note. More importantly for our question, the observations mapped motion in its atmosphere and found turbulent, low-density gas farther from the star than expected. That point is more important than the number. A red supergiant's outer atmosphere is not a quiet, painted shell. It can be extended, moving, and partly detached in behavior from the simple diagram of a round star. If a measurement depends on the layer where light escapes, then the answer can depend on wavelength, model, and time. The photosphere is a physical concept, but it is also a measurement boundary. It tells us where the star becomes transparent enough for light to leave, not where a solid object ends. This is not a technical footnote, it is the heart of the documentary. If the edge is partly a measurement, then the biggest star is partly a measurement problem. The candidates still matter. The numbers still matter. But every number sits on top of a decision about what layer counts as the star. For red supergiants, the outer atmosphere can be so extended that the transition feels especially unlike an edge. Gas does not simply end, density falls. Temperature changes, opacity changes, dust and molecular layers may affect what different instruments see. A radius estimate is therefore tied to the kind of light being measured and the model used to interpret it. The edge problem also changes the emotion of the image. A hard red wall would be simpler but less real. The actual boundary is a glowing transition in gas, a place where opacity falls and light escapes. That makes the star feel less like an object drawn in space and more like a process happening across space. The photosphere is one of the most important words in the whole problem. It names the layer from which light escapes easily enough to travel outward. That layer behaves like a visible surface from far away, but it is not a surface in the ordinary sense. It is a transition in gas. It is a place where opacity changes, not a wall where material stops. In a cool supergiant, that transition can be spread through an atmosphere that is itself enormous. Different kinds of light can trace different depths. Molecular layers can sit above the apparent surface. Dust can form farther out. Winds can carry material away. The radius depends on which physical layer and observational method are being discussed. That is why a precise-looking circle in an animation can accidentally lie. It may be a useful simplification, but it hides the gradual outward fade of density and transparency. For a red supergiant, the question is not only how wide the circle is, it is why that circle was drawn there instead of at another layer. Once the edge becomes a threshold, the biggest star question changes character. The answer is not just a catalogue ranking, it is a question about how light escapes from an unstable atmosphere, how instruments see that light, and how models translate the observation into a radius. The photosphere matters because it translates a physical object into an observable boundary. Light escaping from a layer of gas gives the eye in the telescope something surface-like. Yet the material above and below that layer does not suddenly vanish. In red supergiants, the transition can be broad enough that the word surface becomes a convenience rather than a literal description. This creates a subtle problem for every size comparison. A drawn circle suggests a final contour. The actual star offers a gradual change in opacity and density. Depending on wavelength, molecules, dust, and atmospheric extension, the apparent boundary can shift. The same star can therefore invite different radius estimates without anyone inventing the uncertainty for drama. Antares is useful because it anchors this problem in observation rather than philosophy. Interferometric work on Antares lets the story discuss atmospheric motion and extended gas with a named example. The point is not that Antares wins the contest. The point is that even a relatively familiar red supergiant can have an outer atmosphere more complicated than the smooth sphere in a diagram. The boundary question also reshapes the emotional tone. A solid surface would make the largest star race easier but less revealing. A fading, turbulent, light-defined atmosphere makes the question deeper. It means the largest star is partly about stellar evolution, partly about radiative transfer, partly about instrumentation, and partly about the language humans use to turn gas into an edge. The photosphere is often treated as a surface because it is the layer from which much of the visible light escapes. That is useful, but it is not the same as a rocky crust or a planetary ground. Above and below that layer, gas continues to exist. Density, opacity, temperature, molecules, and motion all influence where the visible boundary appears. In a red supergiant, the outer atmosphere can be so extended that a single edge becomes a simplification. Different wavelengths may probe different layers. Dust and molecules can change the apparent size. Large convective structures and atmospheric motion can make the star less like a perfect sphere and more like a vast changing weather system made of plasma. This is why direct measurements are so valuable. Interferometry can resolve stellar disks and atmospheric structure for selected nearby giants, offering a more concrete picture than an inferred number alone. Even then, the result is not a photograph of a hard edge. It is a measurement of light from a layered atmosphere. Once that is understood, the largest star problem changes character. The question is no longer only which sphere is widest. It is which light-defined boundary is being counted, how that boundary was measured, and how much the outer atmosphere complicates the comparison between one giant and another. The word edge survives because human perception needs boundaries. A drawn sphere has a clean outline, and a radius line needs somewhere to stop. A star, especially an evolved cool supergiant, does not oblige with a solid contour. It becomes optically thin gradually. The radius is tied to where light escapes under a chosen definition, not to a surface that a spacecraft could touch like ground. That subtlety matters because different physical layers can dominate at different wavelengths. Molecular bands, dust, and atmospheric extension can make a star appear larger or smaller depending on how it is observed. The boundary is partly a property of the star and partly a property of the observational method. A single number can be useful, but it is never the whole object. The largest candidates push this problem to an extreme. Their atmospheres are not quiet shells. They are enormous, convective, and sometimes embedded in material lost from the star. A radius estimate becomes a disciplined convention imposed on a changing body. That convention can be scientifically strong, but it must not be mistaken for a cliff at the edge of space. Opacity is the hidden word behind the visible boundary. Deep inside a star, light is trapped and scattered repeatedly. Farther out, the gas becomes transparent enough for radiation to escape. The photosphere marks that transition in a practical way. It is where the star becomes visible to us, not where the star stops existing in an absolute sense. This makes a red supergiant radius similar to a weather boundary more than a coastline. A storm can have a center, a visible shape, and a measurable extent, yet its outer edge fades into surrounding air. A giant stellar atmosphere has far harsher physics, but the analogy helps preserve the idea of a boundary that is real enough to measure and fuzzy enough to argue over. The fuzzy edge is not an excuse to abandon measurement. Scientists routinely measure quantities that require definitions: sea level, cloud tops, planetary atmospheres, galaxy sizes, and stellar photospheres. The act of defining a boundary can be rigorous when the definition is stated and used consistently. The danger comes from hiding the definition. For the largest stars, the boundary is meaningful because it is tied to escaping light, but that meaning is conditional rather than absolute. A star's radius is therefore a practical scientific boundary, not a denial of surrounding material. Gas above the photosphere can still matter through winds, dust formation, absorption, and emission. Some of that material may be gravitationally connected, some may be escaping, and some may already be part of the circumstellar environment. Deciding what counts as the star is part of the intellectual burden carried by the word biggest. The stars that dominate the largest radius conversation are usually evolved massive stars. They were not born as enormous red spheres. They began their lives hot, massive, and much more compact than their later forms. For most of a star's life, the structure is a balance between gravity pulling inward and pressure from hot gas and radiation pushing outward. The core burns through nuclear fuel. The outer layers respond to changes deep inside. When the internal engine changes, the whole star can change shape. After a massive star exhausts hydrogen in its core, it evolves away from the main sequence. The details are complex, but the visual result can be dramatic. The outer envelope expands, the surface cools, the star becomes redder. Its radius can grow until the original main sequence star seems almost like a seed hidden inside a vast atmosphere. The star has not become huge because it swallowed a universe of new mass. It has become huge because its outer layers have inflated. That distinction matters. A red supergiant can be astonishingly wide and still have an outer envelope that is extremely low in density. If it were placed near the Sun in a scale comparison, it might extend beyond the orbits of inner planets. But the outer regions are not solid, and they are not dense like rock, ocean, or even a planetary atmosphere at familiar pressures. They are star material in a late evolutionary state, spread over a vast volume. This is why the largest radius stars often look visually less violent than the most massive stars. A hot blue star can feel more energetic, more brilliant, more dangerous in ultraviolet light and stellar wind. A red supergiant can look calmer in a graphic because it is cooler and redder, but that calm is deceptive. These objects are unstable in deep ways. Their outer layers convect, pulsate, shed mass, and build dusty environments. They are late-stage stars trying to hold themselves together while the internal clock moves toward a more violent future. The largest star candidates belong to this broader family of inflated, evolved, unstable giants. That is the first real answer to the title. We are not looking for the heaviest star. We are not looking for the brightest star. We are looking among stars whose envelopes have expanded into enormous, cool, red, low-density atmospheres. The biggest radius belongs not to the star with the most material, but to the star whose outer layers have been pushed farthest outward under conditions we can still identify and measure. This is already more interesting than a leaderboard. It means the record question is also a life cycle question. The biggest stars are not merely born large, they become large at a particular stage of stellar evolution, and that stage is unstable. The very process that makes them enormous also makes them difficult to measure. That matters for the tone. These stars should not be described as passive ornaments. They are late-stage engines with swollen envelopes and unstable outer layers. Their size is connected to their mortality. The same expansion that makes them visually majestic also places them closer to dramatic future change, including further mass loss and eventually catastrophic endpoints, depending on their mass and evolution. This gives the story an emotional undercurrent. The largest stars are not merely big, they are fragile in a particular astrophysical way. Their atmospheres are huge, diffuse, and dynamic. They impress us not because they are solid, but because they are almost the opposite, vast structures of gas held in a temporary balance. This late-stage expansion also gives the scale a sense of time. The star did not always look this way, and it will not remain this way forever. The largest radius is a temporary condition in the life of a massive star. The record, if there is one, belongs to a moment in an evolution, not to a fixed architecture. The inflation of a red supergiant is not a gentle decorative swelling, it is a structural response to deep changes in the star. As the core evolves, the outer layers adjust, expand, cool, and become luminous over a larger area. The visual result is a star whose radius can become staggering while its outer density remains low. This gives the largest radius stars a paradoxical quality. They are physically immense, but not solidly full. Their outer layers are extended and fragile compared with the compact mental image suggested by a red circle. That is why they are both perfect for scale awe and dangerous for oversimplified graphics. The size is real, but its meaning requires explanation. The late-stage nature of these objects also means their size is tied to instability. The star is no longer in a calm, simple, main-sequence life. It is evolving through a phase where mass loss, convection, pulsation, and changing surface conditions can matter. The enormous radius belongs to a star in transition. That transition is part of the emotional power of the topic. The largest stars are not merely bigger versions of the Sun, they are end-stage structures with swollen envelopes and complicated atmospheres. Their scale is linked to age, exhaustion, and internal rearrangement. The vastness has a clock inside it. This also explains why candidate rankings do not behave like a list of planets by diameter. Planets are comparatively stable, solid, or gaseous bodies with better defined edges. Red supergiants are late-life stellar atmospheres. Their radius can be model-dependent, variable, and entangled with the physical processes that are ending the star's life. The evolutionary story keeps the scale from becoming arbitrary. Red supergiants are not random objects that happen to be wide. They are massive stars in a late phase, after internal changes have forced the outer envelope to expand and cool. The enormous radius is a consequence of structure, fuel, pressure, gravity, and time. That expansion produces a star that can be visually overwhelming while physically delicate in its outer regions. The envelope is not dense like a planet. It is a spread-out atmosphere bound to a dying giant. The star can occupy a volume that dwarfs the inner solar system in a comparison, yet the outer material is thin, dynamic, and vulnerable to mass loss. This late-life context explains why variability belongs in the story. A star with an extended envelope is not a quiet measuring rod. Convection, pulsation, changing brightness, and surface conditions can affect what is observed. The largest radius is not just a static architecture, it is part of an evolving phase that may not last long on cosmic timescales. The comparison with more massive hot stars also becomes clearer here. A blue massive star may be more powerful and contain more material, but it can be physically smaller because its structure and temperature are different. The largest radius contest is therefore not a contest of power alone. It is a contest of expansion. Red supergiants are large because they occupy a particular stage in stellar evolution. After massive stars exhaust core hydrogen and reorganize their interiors, their outer layers can expand and cool. The star becomes physically wide, luminous, and fragile in its outer regions. The size is not decorative. It is a consequence of internal change. That evolutionary context also explains why these objects are unstable measuring targets. Their envelopes are extended, convective, and prone to mass loss. Material can be lifted away from the star and become part of a surrounding dusty environment. The same physical process that creates the enormous radius can also make the radius harder to define. The inflated envelope should not be imagined as a solid container. Its density falls outward. Its outer layers are thin compared with the star's deep interior. A comparison with planetary orbits can be visually accurate as a scale aid, while still hiding the fact that the material near the edge is extremely tenuous. This makes the largest radius stars stranger than simple oversized suns. They are late-life stellar atmospheres extended across distances that overwhelm ordinary comparison, but their greatness is unstable and transitional. Their size is a phase, not an eternal property, and that is part of what makes them scientifically valuable. The evolutionary path matters because it gives the size a cause. Massive stars spend most of their lives balancing gravity against the pressure created by nuclear fusion. As fuel stages change, the interior reorganizes and the outer envelope can expand. The red supergiant phase is not an arbitrary costume. It is a late state of a star whose internal structure has changed profoundly. This expansion produces a paradoxical object, immense in radius, yet fragile in its outskirts. The outer layers can be spread so thinly that ordinary ideas of a body become misleading. The star dominates a huge region of space, but the material near the light-defined edge is rarefied gas. That is why the same object can be visually overwhelming and physically subtle. Mass loss turns the inflated giant into a source of its own confusion. Gas and dust can leave the star and create a surrounding environment. Later observations then have to separate the star from material connected to its history. The object being measured is not isolated like a ball on a table. It is an evolving system with a memory written around it. The red color is a clue to the expanded state. Cooler outer layers emit more strongly at longer wavelengths, while the enormous area keeps the total luminosity high. The star is not dim because it is cool. It is luminous because the emitting surface is vast. Temperature and radius pull in opposite intuitive directions, and the final brightness comes from their combination. The end state of these giants also matters. Many are approaching violent futures, core collapse, heavy mass loss, or dramatic transitions that reshape the surrounding environment. Their huge radii are not permanent monuments. They are late-stage configurations, held for a relatively brief cosmic interval before the star changes again. That temporary quality makes the size more precious, not less. The internal history also explains why the largest stars tend to be rare. Massive stars are already uncommon, and the expanded red supergiant phase is only one part of their lives. The objects that reach extreme radii occupy a narrow evolutionary window. That rarity adds to the uncertainty because the sample is limited. Many cases are distant or dusty, and the most dramatic examples are not always the easiest ones to measure cleanly. If a red supergiant is hundreds or thousands of times wider than the Sun, it seems as if the measurement should be easy. It is not. Even enormous stars are usually so far away that their disks are tiny on the sky. To most telescopes, a star remains a point of light. The information has to be extracted from that light, with methods that are powerful but not magical. The ruler is not a physical ruler. It is angular size, brightness, color, spectrum, distance, temperature, and model. But this direct route is limited. Many of the most extreme candidate stars are too distant, too dusty, too crowded, or too complicated for a simple resolved disk measurement. So astronomers often infer radius from luminosity and effective temperature. The plain language version is this: if you know how much total light a star produces, and you know the temperature of the surface that is radiating that light, you can estimate how large the radiating surface must be. A cooler star has to be larger to produce the same luminosity. A hotter star can produce more light from a smaller area. That method is physically grounded, but every input matters. Luminosity depends on distance. If the star is farther away than assumed, it has to be more luminous to appear as bright as it does. If it is closer, it may be less luminous. Temperature matters because radius is sensitive to it. Dust matters because dust changes how much light reaches us and what color it appears to have. Atmospheric models matter because red supergiants are not simple black bodies with clean surfaces. This is where public rankings often become brittle. A list may take a radius estimate from one paper, one database, or one older summary, then freeze it in a comparison chart. Years later, the distance estimate changes, or the temperature scale changes, or the object is reinterpreted. The old graphic still circulates. The number still looks precise, but the measurement underneath it has moved. The important thing is not to make astronomy feel evasive. A good astronomical answer names what is known and what remains uncertain. Good science does not pretend the uncertainty is absent. It names the method. It names the assumptions. It separates direct measurements from inferred quantities. It treats enormous numbers with respect rather than using them as decoration. Interferometry provides a useful contrast. It can feel almost like building a telescope larger than any one mirror by combining signals across distance. For nearby giants, that can reveal a disk or atmospheric structure. But even then, the interpretation is not a simple photograph of a hard surface. Limb darkening, wavelength, atmospheric extension, and model choices still matter. Direct does not mean assumption-free. That is why a radius estimate is strongest when the measurement path is visible. Distance, temperature, luminosity, wavelength, and atmosphere are not clutter around the answer. They are the answer's support beams. Remove them, and the number may still sound impressive, but it no longer tells us how much confidence it deserves. Every measurement route has strengths and limits. Angular diameter feels closest to measuring size directly, but it still requires distance and interpretation. Interferometry can resolve tiny apparent sizes, yet it does not remove the complexity of an extended atmosphere. The observation becomes stronger, not magically simple. Inferred radius is often misunderstood because it sounds weaker than direct measurement. In reality, inference is one of astronomy's central powers. Light carries information about luminosity and temperature. Physics connects those quantities to emitting area. The problem is not inference itself. The problem is forgetting which inputs shape the inference. Distance sits at the foundation. A star that looks bright at a great distance must be more luminous than a star with the same apparent brightness nearby. Temperature then changes the radius needed to produce that luminosity. Dust changes the observed light before it reaches the telescope. Each correction becomes a lever on the final estimate. That is why large star values can shift without anyone discovering that the star physically shrank. A better distance, a different extinction correction, or a revised temperature scale can move the inferred radius. The measurement improves, and the public number changes. The star remains enormous, but its place in the ranking may not survive. The safest habit is to carry the method beside the number. A radius stated without method can sound like a fact carved into the star. A radius stated with distance, temperature, dust, and uncertainty becomes a scientific estimate. That second form is less tidy, but it is far more trustworthy. A direct ruler cannot be carried to a red supergiant, so astronomy turns light into geometry. The simplest mental version is angular diameter plus distance. Measure how wide the object appears, know how far away it is, and calculate its physical width. In practice, each phrase hides technical work, especially when the object is distant, dusty, variable, and atmospheric rather than solid. Interferometry is the closest this story gets to a visual measuring tool. By combining light collected across separated telescopes, astronomers can resolve details that would otherwise be blurred into a point. That is why interferometric red supergiant studies have such narrative value. They show that the star is not merely guessed from afar. In select cases, its disk and atmosphere can be constrained with remarkable precision. Most extreme candidates, however, are not measured that cleanly. Their radii are often inferred from luminosity and effective temperature. If the star is cool and extremely luminous, physics implies a large emitting surface. But luminosity depends on distance, and temperature depends on spectral interpretation and atmospheric modeling. The final radius inherits those dependencies. Dust adds a practical obstacle. It can dim and redden the light, making the star appear different from its intrinsic output. Correcting for extinction is necessary, but it is not a clerical adjustment. It depends on the dust properties and where the dust sits. Around mass-losing red supergiants, some of the dust may belong to the star's own environment. To estimate a stellar radius, astronomy has to convert received light into physical size. In the cleanest version, angular diameter and distance provide geometry. If the apparent width is known and the distance is known, the true width can be calculated. The hard part is that extreme candidates rarely offer the cleanest version. Many radii are inferred from luminosity and effective temperature. A cool, luminous star must have a large emitting area, so physics gives a radius, but luminosity depends on distance and extinction, while temperature depends on spectral interpretation and atmospheric modeling. The radius is therefore only as strong as the inputs used to derive it. Dust is a major obstacle because it changes the light before it reaches the telescope. Interstellar dust can dim and redden a star. Circumstellar dust from the star's own mass loss can complicate the scene further. Correcting for that dust is necessary, but the correction is part of the evidence, not a harmless afterthought. The instrument also matters. A resolved angular diameter, an infrared measurement, a model atmosphere and a distance estimate do not all carry the same kind of certainty. A number printed in a list can hide those differences. A careful answer brings them back into view before asking which candidate belongs near the top. The measurement chain begins with photons. They leave the star, cross interstellar space, pass through dust and gas, enter instruments, and are translated into spectra, brightnesses, angular constraints, and models. By the time a radius appears in a catalogue, it represents a long conversion process. That process may be excellent, but it is not invisible. It is the foundation of the claim. Effective temperature is one of the most powerful inputs because it links luminosity to area. For the same luminosity, a cooler emitting surface must be larger than a hotter one. This is why temperature uncertainty matters so much for red supergiants. A change in the adopted temperature scale can move the implied radius, especially when paired with uncertainty in extinction and distance. Interferometry gives the story a firmer observational anchor, but even it requires interpretation. Instruments can constrain apparent diameter and atmospheric structure, yet limb darkening, wavelength choice, molecular layers, and extended gas remain relevant. Direct does not mean simple. It means the measurement has a different kind of strength than a purely inferred radius. A radius estimate can be written as if it were a direct fact, but it often rests on several measured and modeled quantities. Brightness has to be corrected for distance and dust. Temperature has to be inferred from spectra and atmosphere models. The resulting luminosity and temperature are then combined through stellar physics. Each step may be reasonable while still contributing uncertainty. This is why error bars and ranges matter more than trophy numbers. A candidate listed at an enormous radius with broad uncertainty may overlap with another candidate listed at a slightly smaller radius but stronger evidence. Rank order becomes less important than confidence. The best answer needs both magnitude and reliability, not magnitude alone. A catalogue value, therefore, should be read like a compressed argument. It may summarize observations, calibrations, models, and assumptions in a single line. That compression is necessary for comparison, but it can hide the difference between a robust nearby measurement and an ambitious inference for a distant, obscured object. The careful habit is to unpack the line before ranking the star. Numbers become more useful when their origins are visible. The strongest measurements combine multiple constraints. Photometry can describe brightness, spectra can constrain temperature and composition, infrared data can reveal dust-obscured energy, and high-resolution techniques can limit angular size. No single tool owns the truth. Confidence grows when different lines of evidence point toward the same physical scale, and when the remaining uncertainty is stated rather than buried. Distance is the quiet lever behind many largest star claims. It does not feel dramatic at first. The star is where it is. Why should the distance be part of the story? But for inferred radii, distance can decide the size. If a star appears with a certain brightness from Earth, then a farther distance means the star must be intrinsically more luminous. A more luminous, cool star may require a larger radius. Bring the same object closer, and the inferred luminosity falls. The estimated radius can fall with it. This is why distance is not a footnote, it is part of the measurement. For nearby stars, parallax can be powerful. As Earth moves around the Sun, the apparent position of a star shifts slightly against the background. Gaia has transformed stellar astrometry by measuring positions and parallaxes for huge numbers of stars. But it does not turn every extreme red supergiant into a solved problem. Very bright, distant, dusty, variable stars in crowded regions can still be difficult. A bad simplification would be to say Gaia makes all these distances easy. It does not. Dust adds another layer. Red supergiants often sit behind dust or create dust around themselves through mass loss. Dust dims light, it reddens light. It can hide stars in visible wavelengths while infrared observations reveal more. Correcting for extinction is necessary, but the correction is model dependent. If the dust correction is wrong, the luminosity estimate can shift. If luminosity shifts, radius can shift. The star itself has not changed. Our reconstruction has. Cluster membership can be just as important. If a star belongs to a cluster, the cluster distance can help set the star's distance. But if the membership is uncertain, the radius claim inherits that uncertainty. This will matter when we talk about Stephenson 218. Its appeal as a modern largest star candidate is tied to where it is, what group it belongs to, and what distance is assumed. Change those assumptions, and the size claim changes. This is one reason famous candidate names are not interchangeable trophies. Scuti, Stephenson 218, WOH G64, VY Canis Majoris, and other extreme stars live in different observational situations. Some are galactic, some are extragalactic, some are dusty, some are variable, some are in complicated regions, some have better direct constraints than others. A fair comparison has to compare not only the numbers, but the routes by which the numbers were obtained. Dust is especially treacherous because it is both an obstacle and a clue. It blocks and reddens light, making the star harder to measure. But it also tells us something about the star's behavior, because evolved massive stars can create dusty material through mass loss. The same environment that hides the star may be evidence of the late-stage instability that makes the star important. Infrared observations help because infrared light can pass through dusty regions more effectively than visible light, and cool stars emit strongly at longer wavelengths. But infrared does not magically remove all uncertainty. It gives a different window. The interpretation still has to account for dust, temperature, distance, and surrounding material. Cluster membership is a story device as much as a measurement issue. If the star belongs to a known group, the group can help anchor the distance and age context. If the star is merely in the same direction but not actually a member, the inferred properties can be wrong. That is exactly the kind of hidden assumption a public size chart usually cannot show. The same star can therefore look different in the public imagination depending on which distance and dust correction became popular. One source may preserve an older assumption, another may use a revised one. The disagreement is not always a scandal. Sometimes it is the natural result of a difficult object being measured better over time. The distance problem becomes especially sharp for red supergiants in crowded or obscured regions. A star may lie in the direction of a cluster without being a secure member. If membership is assumed, the cluster distance can become part of the star's size estimate. If membership later becomes uncertain, the radius claim loses some of its support. Dust complicates the issue because it changes the light before any telescope receives it. Some dust may sit between Earth and the star. Some may belong to the star's own environment. Some may be connected to mass loss. Correcting for dust is not just subtracting a curtain from the image. It requires assumptions about composition, distribution, and wavelength behavior. Infrared astronomy helps by opening a window through dustier regions and by matching the cool temperatures of red supergiants. But an infrared detection still has to be interpreted. The data may improve the case, but the model remains part of the answer. The distance and extinction problem never disappears just because the wavelength changes. Gaia deserves respect and caution in the same breath. It has transformed stellar distance work, but extreme red supergiants can be difficult targets because of brightness, variability, dust, crowding, and distance. A careful treatment does not dismiss Gaia. It simply refuses to pretend that every famous candidate now has a perfectly simple parallax answer. This is the setup for the most tempting modern candidates. Their scale can be breathtaking, but the radius often rests on distance, membership, and extinction. A star can be a legitimate candidate, while still carrying enough uncertainty to make a permanent crown irresponsible. Distance is the lever that can move an inferred radius without changing the star. A faint-looking object might be modest and nearby, or luminous and far away. For a cool giant, a higher luminosity can mean a larger emitting surface. That is why a distance revision can shrink or enlarge a candidate in the rankings, even though the object itself has not physically changed. Crowded regions make this especially treacherous. If a red supergiant lies near a cluster, membership can determine the distance adopted for the star. A secure member inherits the cluster context. A foreground or background object does not. This is one reason Stephenson 218 is so valuable as a case study. The membership and distance assumptions are not decorative details. They help support the entire size claim. Dust and extinction complicate the same calculation from another direction. The observed light is not the original light. It has crossed interstellar material and, in many cases, material created by the star itself. Infrared observations can help reveal obscured giants, but infrared data still require interpretation. A longer wavelength is a better window, not an automatic answer. Distance is one of the strongest levers in the entire problem. If a star is farther away than assumed, its intrinsic luminosity may be larger. If it is closer, the same observed brightness can imply a smaller object. For radius estimates built from luminosity, distance revisions can move a candidate dramatically without the star itself changing at all. Crowded stellar regions add another layer. If a giant is believed to belong to a cluster or association, that membership can anchor the distance used in the calculation. If the membership is uncertain, the radius becomes less secure. The issue is not a minor catalogue detail. It can be central to whether a star looks extreme or merely very large. Stephenson 218 sits directly inside this kind of problem. Its status as an extreme candidate depends on the adopted context, including distance and association. That makes it compelling, but it also means the public claim cannot be separated from the technical conditions underneath it. The assumptions are part of the answer. Modern astrometry has improved many stellar distances, yet not every red supergiant becomes easy. Brightness, crowding, dust, variability, and extended atmospheres can all interfere with clean measurement. Better data narrows uncertainty, but it does not erase the fact that the largest candidates often sit at the edge of what the methods can comfortably support. Distance turns apparent faintness into intrinsic power. A star can look modest because it is genuinely modest, or because it is far away and dimmed by dust. For an inferred red supergiant radius, the adopted distance helps determine luminosity, and luminosity helps determine size. Move the distance, and the radius can move with it. Cluster membership is therefore more than bookkeeping. If an object belongs to a cluster or association at a known distance, the calculation gains a foundation. If it is a foreground or background interloper, the foundation changes. In crowded stellar fields, deciding where a star belongs can be part of deciding how large it is. Extinction and reddening deepen the problem. Dust can hide blue light, alter colors, and make the star appear cooler or dimmer than it would in a clear line of sight. Correcting for that effect requires assumptions about dust properties and geometry. Around mass-losing red supergiants, some dust may be local to the star itself, making the correction physically connected to the object under study. Parallax is powerful because it gives geometry rather than assumption, but extreme supergiants are not always ideal parallax targets. They can be distant, bright, variable, dusty, or embedded in crowded regions. Measurement precision that works beautifully for many stars can become harder near these luminous evolved objects. The frontier cases remain frontier cases for practical reasons. A distance debate can sound abstract until its effect is translated into radius. If the star is placed farther away, the observed light must represent a more luminous object, and a cool luminous object generally needs a wider emitting surface. If placed nearer, the inferred size can contract. The record can change because the ruler changed, not because the star physically shrank. The same distance issue explains why older record claims can remain emotionally sticky. A dramatic radius, once repeated, feels like a property of the star itself. Later distance work may make the number smaller or less secure. Yet the old comparison continues to circulate because it was memorable. The physical object did not betray anyone. The interpretation improved, and public memory took longer to catch up. Distance also explains why uncertainty is not evenly distributed. A relatively nearby red supergiant with strong constraints may have a less spectacular radius, but a cleaner measurement. A remote, dusty candidate may have a more spectacular radius, but a wider confidence range. The comparison is therefore two-dimensional: how large the candidate may be, and how securely that largeness has been established. Red supergiants are not static measuring rods. They are unstable, evolving stars with enormous outer layers. Their brightness can vary, their surfaces can shift, their apsospheres can convect and pulsate. They can shed mass into space and surround themselves with dust. The very properties that make them visually spectacular also make them difficult to reduce to one permanent radius. Imagine trying to measure the edge of a storm cloud from far away, while the cloud is changing shape, while dust is moving between you and it, and while your measurement depends on which color of light you use. That is not a perfect analogy, but it catches the problem. The target is real. The measurement is real, but the target is not a rigid object. This is where the phrase, "where does a star end?" becomes physical rather than philosophical. In a normal size chart, the star is drawn as a circle. In reality, a late-stage giant may have an atmosphere, winds, dusty material, and changing layers. Some of that material is still influenced by the star. Some of it is leaving. Some of it absorbs and re-emits light. Depending on the observation, the object can appear different. The largest star question, therefore, has a time dimension. A radius estimate is not a timeless inscription carved into the object. It is a measurement made with particular data at particular wavelengths, interpreted through particular models. If the star varies, or if later observations improve the distance, or if the temperature scale changes, the answer may move. This should make the candidates feel more impressive, not less. A rigid red ball is visually simple. A vast, unstable atmosphere, swollen by late-stage stellar evolution and leaking material into space, is stranger. The biggest stars are not merely large. They are in the act of becoming, shedding, dimming, brightening, and approaching the end of their lives. The measurement problem is part of their nature. Variability also complicates the emotional idea of a record. A record suggests a fixed value, but if the star's brightness and temperature change, the inferred radius may not be identical at every epoch. The star can be observed at one time and modeled one way, then observed later with better data or under different conditions. The result is not necessarily contradiction. It can be time entering the measurement. Mass loss matters because it creates a surrounding environment that can glow, absorb, scatter, and re-emit light. Around extreme evolved stars, the space near the star may contain material that was recently part of the star's outer layers. When a public graphic draws a boundary, it usually cannot show that ambiguity. The real object may have a central photosphere, extended atmosphere, wind, and dusty structures all participating in what we observe. A moving target asks for repeated humility. The question is not only how big the star is, but when it was observed, in which light, through which dust, and under which model. A single radius can be useful, but it is never the whole story for an unstable giant atmosphere. Variability turns a radius estimate into a snapshot rather than a monument. A red supergiant can change brightness and surface conditions across time. When luminosity or temperature changes, the inferred radius may shift as well. The object being measured is real, but it is not frozen for the convenience of the ranking. Mass loss adds another complication. Material leaving the star can form dust and gas structures around it. Those structures can absorb, scatter, or re-emit light. They can also blur the intuitive boundary between the atmosphere and the surrounding environment. Around an extreme evolved star, the space nearby may carry the memory of the star's recent behavior. Betelgeuse offers a familiar way into this point because its dimming became public. It demonstrated that a red supergiant can change in ways visible to ordinary observers and significant to interpretation. The lesson is not that Betelgeuse is the largest. The lesson is that giant star surfaces and atmospheres are dynamic. WOH Canis Majoris gives the same lesson in a more extreme environmental form. Its surrounding material and heavy mass loss reputation make it valuable for explaining why an outer boundary can be difficult to define. The star is not only a central photosphere, it is a source of material, dust, and structure. A record based on a moving target must be handled carefully. The radius can be useful, but the time, wavelength, and model matter. A calm answer admits that the largest stars may be measured more like changing atmospheres than like objects on a shelf. The target is moving in more than one sense. A red supergiant evolves over time, varies in brightness, shifts in surface conditions, and can expel material into its surroundings. That means a measurement is tied not only to method but also to epoch. The star observed today may not present exactly the same brightness or atmospheric state as the star observed later. WOH Canis Majoris pushes the environment problem further. Heavy mass loss and surrounding material make it a strong example of how a star can shape its own observational difficulty. Dust and expelled gas can become part of the scene the telescope must interpret. The star's history is written around it, and that history can affect the light. Variability also challenges the psychology of records. A record invites a fixed number. A changing stellar atmosphere invites a range, an epoch, and a model. Those are not excuses, they are the correct way to talk about an object whose outer layers are physically active. A red supergiant is not a rigid ball waiting to be measured once. It varies, convects, sheds material, and changes brightness. Its outer atmosphere can shift over time, and the surrounding environment can carry traces of earlier mass loss. A radius estimate is therefore tied to both method and epoch. Betelgeuse made this principle familiar when its dramatic dimming drew public attention. The event did not make Betelgeuse a largest star champion, but it showed that red supergiants can change in ways large enough to be noticed far beyond specialist circles. The surface conditions of such stars are active, not frozen. WOH Canis Majoris demonstrates the surrounding material problem especially well. It is famous not just for size, but for mass loss and complex dusty structures around it. The star has written part of its history into the space nearby, and that material can shape how the central object is observed. This variability changes how record language should sound. A fixed crown implies a stable object and a settled measurement. The real situation is better described with ranges, assumptions, and time-specific observations. The target moves because the star evolves, and the target moves because the interpretation improves. The outer layers of a red supergiant are alive with motion. Giant convective cells, pulsation, changing opacity, and episodes of mass loss can all alter what the star presents to space. A measurement taken at one time does not necessarily capture every state the object can occupy. The radius belongs to a physical moment as well as a method. Variability also changes public intuition. People often imagine stars as fixed points, slowly evolving only over vast timescales. Red supergiants can complicate that picture. Their brightness and atmosphere can vary enough for repeated observations to matter. The star is still governed by long stellar evolution, but its outer behavior can be active on shorter humanly tracked intervals. Material around the star can preserve evidence of earlier instability. Dust shells, arcs, clumps, or asymmetric structures can reveal mass loss that has already happened. Observing the central star through that environment is like measuring a lighthouse through fog it helped create. The signal is real, but the surroundings matter. Pulsation adds another kind of motion. As the outer layers expand and contract, temperature and brightness can shift. The star remains the same object, but the measured properties may not be identical from one observing campaign to another. A radius attached to an epoch is not a weakness. It is a more faithful description of an active giant. Asymmetry complicates the mental sphere. Large convective cells and uneven mass loss can make the outer environment irregular. A single average radius may still be necessary for comparison, but the star itself may not behave like a smooth ball. The comparison graphic is a simplification overlaid on a physically lumpy and restless atmosphere. The motion also affects how confidence should sound. A red supergiant can be described with a representative radius, but the phrase should leave room for variability and extended structure. Precise language does not need to be clumsy. It can say estimated, approximate, model-dependent, or among the largest when those words carry real information. Precision in wording is part of precision in science. A moving target also makes archival values tricky. An older measurement may have been careful for its time, but it captured a star under specific assumptions and conditions. Later work may not simply replace it with a better number. It may reveal that the object itself behaves in ways that demand a range. The history of the measurements becomes part of the story of the star. Why can such a dramatic change happen? Because the radius depends on distance, luminosity, temperature, dust, and model. If any of those inputs is revised, the radius can change. The older number was not a stone monument. It was an estimate inside a chain of assumptions. The public internet often strips away that chain and preserves only the most exciting result. This is not a reason to mock people for knowing the old answer. It is a reason to bring people with us. Scuti was famous for a reason. It belongs in the history of the biggest star question. It taught millions of people that stars could become absurdly large, but it also teaches a second lesson. A name can remain famous after its claim has weakened. The cultural answer and the current scientific answer are not always the same. In the structure of this documentary, Scuti should appear as a trust-building correction. We are not saying, forget this star. We are saying, watch what happened to the certainty around it. The object is real. The awe is real. The number was conditional. Once the conditions changed, the ranking changed too. That is the first candidate case study. It clears the ground for the modern temptation. If Scuti is no longer the easy champion, the internet often reaches for another name, one that sounds even more dramatic and less familiar, Stephenson 218. It is one of the best examples of why the biggest star question remains alive. It is also one of the best examples of why the answer cannot be reduced to a winner reveal. Scuti also shows how science communication ages. A number that was plausible or widely repeated in one era can become a cultural fact even after the scientific context changes. Search results, old videos, infographics, and copied articles can preserve a former ranking long after more cautious estimates appear. The internet is very good at remembering drama. It is less good at remembering uncertainty. Scuti remains enormous under any reasonable public discussion. The point is not to shrink it into insignificance. The point is to separate enormous from confirmed largest. That separation is one of the central skills the story gives people. This is the cleanest lesson from Scuti. A star can be genuinely enormous and still lose the public crown. The correction does not make the object boring. It makes the measurement more honest. The old internet answer becomes a doorway into better science. The better treatment is not to humiliate the old claim. The better treatment is to show the mechanism behind the change. Distance, temperature, and luminosity estimates affect radius. Dust and variability complicate the object. Public summaries may update unevenly. A famous answer can become a fossil of an earlier measurement state. This keeps Scuti inside the story rather than throwing it away. The star is still enormous. It still belongs among the memorable large star candidates. What changes is the certainty around its rank. Enormous does not mean final. Famous does not mean current. Old public confidence does not equal present evidence. The older, very large radius associated with Scuti circulated widely because it was visually irresistible. It made comparison graphics spectacular. Later summaries often present smaller values, and the precise current number should be handled carefully, but the lesson is robust. A public champion can lose its certainty when distance, temperature, or modeling changes. That does not make Scuti ordinary. It remains a huge red supergiant candidate and a meaningful part of the largest star conversation. The correction is about rank and confidence, not about stripping the star of grandeur. A star can be one of the largest known and still not deserve the definite article. Scuti became famous because it offered the public a clean answer. The name was memorable enough to repeat. The estimated size was enormous enough to visualize, and comparison charts made it feel definitive. For many people, it became the largest star in the universe by cultural momentum. The scientific lesson is not that Scuti was imaginary. It is a genuine red supergiant and remains a remarkable object. The lesson is that older radius estimates can be revised when distance, temperature, extinction, or modeling changes. A star can remain enormous while losing its claim to a simple crown. That distinction matters because corrections are often mistaken for debunking. A smaller or less certain value does not make the object ordinary. It makes the record claim less secure. The grandeur of Scuti survives, but the public habit of naming it as the final answer does not survive the same way. Scuti is therefore the bridge between internet certainty and astronomical caution. It shows how a measurement can become a meme, how a meme can outlive its caveats, and how returning to the evidence can make the story better rather than smaller. The Scuti story is powerful because it demonstrates how an answer can be both rooted in real science and overstated in popular use. A very large estimate entered public circulation, gained authority through repetition, and became a shortcut for the entire topic. Later caution did not erase the star, it changed the confidence attached to the crown. This distinction is essential. A revised radius does not turn a giant into a normal star. It only changes where the object belongs in a ranking. Scuti remains a dramatic red supergiant, but the strongest current telling should not depend on an old value being treated as final. Grandeur survives without certainty. The same pattern can happen again with any modern candidate. A new name can rise because a paper, press release, or database value looks extreme. The public version then hardens into a simple answer. The cure is a habit, not a replacement name. Check the method before trusting the crown. The older Scuti claim is a reminder that record tables age. A number can be perfectly useful in one context and then become outdated when better constraints arrive. The trouble begins when the old number detaches from its context and becomes a permanent answer in public circulation. Science moved, but the simplified fact stayed behind. A graceful correction keeps both truths. WOH Scuti is still immense, and the former certainty around its rank is no longer the safest way to speak. That balance matters because it avoids a false swing from hype to dismissal. The star does not need to be the champion to remain one of the great examples of red supergiant scale. This is why WOH Scuti remains valuable even after the simple crown fades. It teaches the life cycle of a public space fact. A striking value appears, spreads, hardens into trivia, then meets newer constraints. That life cycle will repeat with other objects if the same habits continue. The durable lesson is not that old names should be discarded. It is that every name should keep its measurement history attached. Stephenson 2.18, also discussed under designations such as Stephenson 2 DFK1, is the star that wants to be the answer. It has the right ingredients for a modern internet champion: an extreme claimed size, a mysterious catalogue-style name, and enough distance from ordinary public knowledge to feel like a secret record. Many public videos and summaries treat it as the largest known star. That is exactly why it has to be handled carefully. The safe version is this. Stephenson 2.18 is often cited as a largest star candidate, but its claim depends on assumptions. It is associated in many discussions with the Stephenson 2 or RSGC2 region, a rich area of red supergiants. Its distance, cluster membership, luminosity, temperature, and derived radius all matter. If it is a member of the cluster at the assumed distance, the inferred properties can become extreme. If the membership or distance is wrong, the size claim changes. This is not a minor caveat, it is the case study. This does not mean Stephenson 2.18 is uninteresting or fake, quite the opposite. It is interesting because it sits near the boundary of what can be claimed responsibly. It may be among the most extreme known candidates under some assumptions. It may deserve a place near the top of a conditional list. But the phrase confirmed largest star carries more certainty than the evidence should bear. The stronger story is not that Stephenson 2.18 wins. The stronger story is that it shows why winning is hard to define. That distinction is the maturity of the story. A weaker documentary would build to Stephenson 2.18 as a final reveal. A stronger one puts it in the middle and lets it teach the method. By that point, the most clickable answer has become the answer that most needs caveats. This is also the best place to explain why derived radii can become spectacular. A cool, effective temperature combined with a very high luminosity produces an enormous radius. But luminosity depends heavily on distance and extinction correction. If the star is not where the extreme interpretation places it, the radius changes. The drama is in that dependency. Stephenson 2.18 is powerful because it forces a choice between drama and discipline. The dramatic version names a winner. The disciplined version shows why the winner depends on membership, distance, extinction, temperature, and modeling. The second version is stronger because it can survive scrutiny. Stephenson 2.18 has a special narrative pull because it seems to offer the answer after WOH Scuti becomes less certain. It feels like the upgraded champion, larger, stranger, more modern, and less familiar. That is exactly why it must be treated with more care rather than less. The central issue is not whether Stephenson 2.18 is impressive. It is. The issue is what has to be true for the most extreme size claim to hold. The object's identity, its relation to the Stephenson 2 region, its distance, extinction, luminosity, and temperature all shape the inferred radius. The candidate is a chain, not a single number. This makes it one of the strongest teaching cases in the whole subject. A public ranking can show the name and the radius. A scientific explanation has to show the supports under that radius. If one support shifts, the final value can shift. If enough supports remain uncertain, the crown must remain conditional. The phrase confirmed largest is therefore the wrong endpoint. A more accurate endpoint is that Stephenson 2 the 18th of may be among the most extreme known candidates under particular assumptions. That sentence preserves the awe and removes the false certainty. It lets the star remain extraordinary without forcing it to carry more proof than the evidence allows. Placed in the middle of the story, Stephenson 218 becomes more useful than a final reveal. It turns the largest star question into an evidence audit. The most clickable candidate becomes the best demonstration of why the biggest star cannot be named responsibly without conditions. Stephenson 218 has become the modern magnet for the largest star claim because it feels like a hidden record. The name is technical, the proposed scale is extreme, and the object sits in a context that sounds remote enough to be mysterious. Those qualities make it perfect for a winner reveal, and dangerous for exactly the same reason. The responsible version keeps the candidate powerful but conditional. The star's status depends on identification, association with the Stephenson 2 region, distance, extinction, luminosity, and effective temperature. Those are not small print caveats after the dramatic number. They are the scaffolding that creates the number in the first place. Designation confusion also belongs in the story because it shows how real catalogue work differs from public naming. Stephenson 218, Stephenson 2 DFK1, and related labels are not branding details. They are reminders that the object lives in a technical literature with cross-identifications, crowded fields, and evolving interpretation. Stephenson 218 attracts attention because it appears to offer the replacement crown. The proposed scale is extreme, the name sounds obscure, and the object sits in a context that invites mystery. It has all the ingredients of a dramatic reveal. It also has exactly the conditions that require caution. The radius claim depends on the adopted distance, extinction, luminosity, temperature, and association with the surrounding stellar region. If those supports hold, the object may belong among the most extreme known radius candidates. If any support shifts, the rank can shift with it. The number cannot be detached from the scaffolding. This is why Stephenson 218 should remain a case study rather than a crowned winner. It may be extraordinary, but extraordinary is not the same as settled. The proper language is conditional. Under certain assumptions, it is one of the strongest candidates for the largest known stellar radius. That conditional phrasing is not timid, it is more precise than the winner version. It lets the star remain vast, while refusing to hide the uncertainty that makes it scientifically interesting. The temptation is to end the search with a name. The stronger move is to show why the name still depends on a measurement chain. Stephenson 218 is compelling precisely because it seems to satisfy the hunger for a new answer. It appears remote, technical, and extreme. The proposed scale is large enough to dominate comparison graphics. Yet, the very ingredients that make it exciting also make it method-sensitive. Distance, membership, extinction, luminosity, and temperature all matter. The cleanest phrasing is conditional and still dramatic. Under certain assumptions, Stephenson 218 belongs among the most extreme known radius candidates. That sentence carries more truth than a trophy sentence. It allows the star to remain astonishing while keeping the support beams visible. The number is not floating alone, it is held up by the measurement chain. This candidate is also useful because it exposes the difference between evidence and appetite. The appetite wants a final name. The evidence offers a strong case with dependencies. If the dependencies become stronger, the case becomes stronger. If they shift, the rank may shift. That is not failure. It is how uncertain frontier measurements behave. The Stephenson 2 region also makes the problem spatially concrete. A star's association with a cluster or group affects the distance used to interpret its light. If the connection is strong, the extreme radius claim gains support. If the connection is weaker, the claim becomes less secure. The identity of the environment is therefore part of the measurement, not background decoration. The name itself carries a lesson. Catalogue designations can make an object sound more authoritative simply because they are technical, but technical naming is not the same as settled ranking. The evidence still has to do the work. Stephenson 218 can remain one of the most fascinating candidates precisely because the support structure is visible and testable. A conditional Stephenson 218 answer can still deliver scale. The object does not need absolute certainty to be astonishing. If its adopted parameters place it near the top of known stellar radii, that is already extraordinary. What must be avoided is the slide from extraordinary candidate to settled champion. The former is supported by cautious evidence. The latter often belongs to the appetite for a clean ending. The most honest treatment lets the candidate carry suspense without forcing a verdict. If future distance and atmosphere work strengthens the case, Stephenson 2, the 18th of May, remain near the top with greater confidence. If the assumptions weaken, the rank may fall while the object remains huge. Either outcome is scientifically coherent because the claim has been tied to evidence rather than myth. The value of WOH G64 is not that it gives us a simple replacement champion. It shows record churn. It shows how new observations, better modeling, and different samples can move candidates into and out of public attention. It also shows why extragalactic red supergiants are both useful and difficult. The Large Magellanic Cloud has a better known overall distance than many individual galactic objects, but the star itself can still involve dust, structure, possible companion effects, and model-dependent radius estimates. The details need strong source verification before precise claims are made. WOH G64 broadens the geography of the question. The largest star conversation is not confined to familiar Milky Way names. Surveys of nearby galaxies can reveal extreme red supergiants too. That makes the universe feel larger in the right way. Not just one hidden champion, but populations of evolved massive stars spread across galaxies, each requiring careful measurement. It also introduces a different kind of public confusion. When a new paper, image, or summary highlights an extreme object, the internet can translate that into a simple record headline. But scientific language often says candidate, estimated, modeled, possible, or among the largest. Public language often says biggest. The gap between those phrases is where misinformation enters. WOH G64 also reminds us that the largest known star is not necessarily hiding in the most familiar part of the sky. The search crosses galaxies, wavelengths, catalogues, and models. That breadth makes a single final crown feel less like science and more like a shortcut. WOH G64 changes the setting by moving the record conversation into the Large Magellanic Cloud. That broadens the scale of the search and prevents the answer from becoming a purely Milky Way argument. It also introduces a different measurement environment where extragalactic context and object-specific modeling both matter. The Large Magellanic Cloud has advantages as a population laboratory, but a dusty evolved star inside it can still be complicated. Distance to the galaxy is not the same thing as a perfectly known radius for every object within it. Dust geometry, atmosphere modeling, possible structures, and interpretation all remain relevant. This is why new largest language can be dangerous. It turns a candidate into a headline before the conditions are understood. WOH G64 may be discussed among the largest candidates under some estimates, but that is not the same as a clean replacement crown. The uncertainty problem follows the candidate across galaxies. The value of WOH G64 is that it shows the field remains active. Candidate lists change as samples improve and models develop. A record can churn not because astronomy is careless, but because the objects are hard and the measurements become better. That churn is part of the truth. By including WOH G64, the answer becomes less provincial and more honest. The largest star problem is not a duel between two internet names. It is a wider measurement landscape across evolved stars, dusty environments, and changing source interpretations. WOH G64 widens the field beyond the Milky Way and shows how record conversations evolve as observations improve. Its location in the Large Magellanic Cloud gives the story a different scale and a different kind of uncertainty. The object is not merely another name on a list. It is a reminder that the largest star question is being asked across galaxies and stellar populations. Extragalactic context can help and complicate at the same time. The distance to the Large Magellanic Cloud is a strong astronomical anchor compared with many messy individual galactic distances, but an individual evolved star can still involve dust, geometry, atmosphere, and model dependence. A well-known host galaxy does not turn every radius inside it into a simple measurement. The star also helps prevent the structure from collapsing into UY Scuti versus Stephenson 218. The largest radius problem is broader than 2 Internet names. It includes survey limits, extragalactic samples, dusty evolved stars, and changing models. New candidates can emerge because the science is active, not because the previous story was fake. WOH G64 expands the search beyond the Milky Way and into the Large Magellanic Cloud. That matters because it shows the largest star question is not locked to a familiar handful of galactic names. Extreme evolved stars can be studied in neighboring galaxies, where distance, environment, dust, and modeling create a different evidentiary pattern. The Large Magellanic Cloud gives astronomers a comparatively strong distance context, but an individual evolved star remains complicated. Its dust, geometry, temperature, luminosity, and circumstellar environment still have to be interpreted. A better-known host distance does not make the stellar boundary automatically clean. New champion language can be useful for attention and dangerous for accuracy. A candidate can enter the top tier without becoming a permanent answer. The phrase "among the largest" may sound less dramatic than the largest, but it carries the truth more cleanly when the measurement is model-dependent. WOH G64 also proves that the list is not static. Better observations can elevate some objects and weaken others. That movement is not a failure of astronomy. It is how knowledge improves when uncertain measurements are replaced by stronger ones and old assumptions are tested against new data. WOH G64 changes the geography of the search. A star in the Large Magellanic Cloud forces the question beyond familiar Milky Way examples and into a neighboring galaxy. That broadens the emotional scale as well as the scientific one. The largest star problem is not confined to the names that circulate most often online. Its host environment offers advantages and complications. A galaxy-scale distance can be better constrained than some individual galactic cases, but the star itself remains an evolved, dusty, complex object. Luminosity, temperature, geometry, and circumstellar material still have to be interpreted. A stable host distance is not the same as a perfectly known stellar radius. The phrase "new champion" should therefore be used with restraint. It can point toward a candidate worth attention, but it can also imply a certainty the evidence may not support. Better observations can move WOH G64 or any similar object upward or downward. The durable lesson is not the latest crown, it is the active nature of the search. An extragalactic candidate also changes the observing strategy. Infrared data, dust modeling, and assumptions about evolved star atmospheres become central. The object may be easier in one respect because its host system has a known distance scale, and harder in another because its own envelope and dust geometry are complex. The balance of strengths and weaknesses is different from a galactic case. The broader lesson is that new candidates should be welcomed without being overpromised. A stronger survey, a sharper instrument, or a better model can reveal an object that deserves attention. That does not automatically create a final answer. It adds a new piece to a comparison that must still separate radius, confidence, and definition. The arrival of new contenders also changes the emotional rhythm of the question. Instead of one final reveal, the subject becomes an evolving frontier. Each strong candidate sharpens part of the method: distance for one, dust for another, atmospheric modeling for another, direct resolution for a nearer example. The answer becomes a network of evidence rather than a single red sphere at the top of a poster. This is the healthy version of record churn. It is not a sequence of failures, but a sequence of refinements. Each candidate forces the methods to become clearer. Each revision exposes which assumptions mattered most. A mature answer can welcome a new extreme object while still asking whether the measurement is strong enough to carry the phrase "largest known star." Some of the most useful stars in this documentary are not the most likely champions. They are the stars that teach the measurement. Betelgeuse, Antares, and WOH Canis Majoris belong in the story because they make the physics visible. They show variability, extended atmospheres, mass loss, dust, and the difference between a clean diagram and a real evolved star. WOH Canis Majoris brings the dust and mass loss problem into focus. It has long been discussed as one of the extreme evolved stars, surrounded by material and associated with heavy mass loss. The exact object-specific phrasing should be checked against strong sources before final approval, but its narrative role is clear. It shows that the boundary of a giant star may be entangled with material the star has thrown outward. Together, these stars prevent a shallow ranking structure. They remind us that the largest star question is really a question about late-stage stellar physics. What happens when a massive star expands? What happens when the surface cools and the envelope becomes enormous? What happens when gas moves above the photosphere? What happens when dust forms around the star? What happens when the star varies while we measure it? This part can also reinforce that not every useful example has to be a record holder. In science communication, the best teaching object is sometimes not the most extreme object. It is the object where the evidence is clearest. That is why Antares can matter more to the argument than a larger but less cleanly constrained candidate. Teacher stars anchor the story because they make the abstract problem observable. Antares may not be the largest champion, but the ESO work gives a concrete example of a red supergiant atmosphere being studied in detail. That evidence helps explain why a star's outer boundary can be turbulent, extended, and physically messy. Betelgeuse provides a different kind of anchor, familiarity. Its dimming showed the public that a red supergiant can change. The star becomes a doorway into variability, surface conditions, and the danger of treating giant stars as static red circles. It is useful not because it wins, but because it makes change imaginable. WOH Canis Majoris adds the mass loss and circumstellar material lesson. It helps explain why the environment around an evolved giant can matter for what is observed. Dust and expelled gas are not decorative background. They can affect the light, the interpretation, and the emotional sense of where the star ends. These teaching examples also prevent the narrative from becoming too dependent on candidates with uncertain records. A strong measurement anchor can be more valuable than a weakly constrained champion. The cleanest evidence is not always attached to the most extreme object, and a careful story makes room for both. WOH Canis Majoris supplies the mass loss and dusty environment lesson. It shows why material around an evolved star can complicate the observational boundary. A giant star may be surrounded by evidence of its own instability, and that surrounding material can influence how the object is seen. Betelgeuse, Antares, and WOH Canis Majoris help explain the physics behind the headline candidates. None needs to be crowned for their presence to matter. Each one makes a different part of the measurement problem concrete. Variability, direct atmospheric study, and dusty mass loss. Betelgeuse provides familiarity. Its changing brightness showed that a red supergiant can behave visibly over human timescales. That makes it a useful entry point into the idea that the outer layers of giant stars are dynamic and that a single value may not capture every relevant state. Antares provides the measurement anchor. Interferometric work reveals a red supergiant atmosphere as a physical structure that can be studied. The lesson is not that Antares is the largest. The lesson is that resolving a stellar atmosphere can expose motion, extension, and complexity behind the simple word, radius. WOH Canis Majoris provides the environmental anchor. Its mass loss and surrounding material show how a giant can complicate its own measurement. The star is not isolated from the matter it has expelled. That surrounding matter becomes part of the observational challenge. Betelgeuse makes the physics personal because it is bright, nearby by astronomical standards, and familiar in the night sky. Its changing behavior has made red supergiant variability tangible. It does not need to be the largest to be useful. it shows that a giant star can be both well-known and physically restless. Antares brings the measurement problem closer to direct observation. Interferometric studies reveal atmospheric structure and motion, rather than a perfectly smooth edge. That makes Antares a teaching star, not because it tops the ranking, but because it shows what kind of object a radius estimate is trying to summarize. WOH Canis Majoris brings dust and mass loss into focus. Its surrounding material demonstrates that evolved giants can alter their own observational environment. The star is not merely a point with a label, it is a central object embedded in the consequences of its own late-stage behavior. That makes the radius question more physical and less like a clean scoreboard. These teaching examples keep the search grounded in real phenomena. Variability is not an abstract caveat when Betelgeuse has visibly changed. Atmospheric structure is not an abstract caveat when Antares can be studied with interferometry. Dust and mass loss are not abstract caveats when WOH Canis Majoris is surrounded by material tied to its own history. The teaching stars also show why the largest candidate is not always the most educational object. A somewhat smaller star with stronger observations can explain the physics more clearly than a more extreme object with weaker constraints. Both kinds of object matter. One supplies the edge of the ranking, and the other supplies the confidence needed to understand the ranking. The teaching examples also protect against a shallow ranking. A less extreme but better understood star can provide the key to interpreting a more extreme but uncertain one. Antares can teach atmospheric extension, Betelgeuse can teach variability, and WOH Canis Majoris can teach mass loss. Those lessons then travel back to Stephenson 218, WOH G64, UI Scuti, and any future candidate with a spectacular radius claim. Now we can answer the title honestly. If biggest means largest estimated radius among known stable stars, then the leading candidates are extreme evolved red supergiants and hypergiants. Names such as Stephenson 218 or Stephenson 2 DFK1, WOH G64, UI Scuti, WOH Canis Majoris, and other extreme red supergiant candidates belong in the conversation. But the responsible answer is conditional. It depends on distance, temperature, dust, variability, cluster membership, atmospheric structure, and where we count the photosphere. That may sound less satisfying than a crown, but it is actually the deeper answer. A crown would hide the most interesting part. The largest star question becomes scientifically rich precisely because the object being measured is not a hard sphere. It is a vast, unstable atmosphere around an evolved star, observed across enormous distances, often through dust, often with indirect methods. The uncertainty is not a failure of the story. It is the story. The safest final language is this. Under some methods and assumptions, several extreme red supergiants or hypergiants are leading candidates for the largest known stellar radius. Stephenson 218 is often cited and may be among the most extreme candidates, but it should not be declared the confirmed largest without the assumptions attached. UI Scuti remains an important famous candidate and a lesson in revised estimates. WOH G64 shows how new candidates and modeling can shift public attention. WOH Canis Majoris shows the messy outer environment of extreme evolved stars. Antares and Betelgeuse teach us how real red supergiants behave. What would it take to make the answer cleaner? Better distances, better temperature estimates, better dust corrections, better models of extended atmospheres, more direct angular constraints where possible, repeated observations across time and wavelength, clearer object identification in crowded fields. In other words, the answer improves not by choosing the most dramatic number, but by strengthening every link in the measurement chain. The final answer should therefore feel like a door opening rather than a door closing. There may not be one permanent, cleanly confirmed biggest star. There are leading candidates, there are methods, there are uncertainties. There are red supergiants so large that ordinary planetary scale becomes useless. And there is a deeper lesson. Sometimes the most honest answer to a cosmic record is not a name, but a map of what has to be measured before the name can mean anything. The closing lesson is that measurement is part of awe. The universe is not made more beautiful by exaggeration. It is made more beautiful by the fact that careful instruments, models, and arguments can reach across thousands or tens of thousands of light years and ask where a fading atmosphere becomes space. The honest answer keeps the awe and removes the false certainty. The candidates are still immense. The sun is still reduced to a marker. The difference is that the final claim now carries its measurement conditions with it. The final answer, therefore, has to be conditional without feeling evasive. There are leading candidates. There are extreme red supergiants and hypergiants with estimated radii so large that ordinary solar system comparisons struggle to stay meaningful. But a responsible answer attaches those candidates to assumptions rather than pretending the assumptions are invisible. If the definition is largest estimated radius among known stable stars, then the likely arena is clear. It is the realm of cool evolved supergiants and hypergiants, not the realm of the most massive hot blue stars. But within that arena, exact ranking can depend on distance, temperature, dust, atmospheric structure, variability, and measurement method. This is why the answer is better as a set of candidates than as a permanent trophy. WOH Scuti, Stephenson 218, WOH G64, VY Canis Majoris, and other extreme objects each reveal part of the truth. Some may be larger under one set of assumptions, some may be better measured, some may be more famous than their present evidence deserves. The absence of a single clean crown is not a failure of scale. It is a sign that the universe is being measured honestly. A false crown would be simpler, but it would also be weaker. A conditional answer can survive new data because it already admits what new data might change. The strongest final impression is that the biggest star is both an object and a boundary problem. It is a real population of enormous evolved stars, and it is also a question about where light escapes, how distance is known, how dust is corrected, and how much certainty a radius estimate can carry. The honest answer can now be stated without apology. If biggest means largest estimated radius among known stable stars, the leading candidates are extreme evolved red supergiants and hypergiants. Names such as Stephenson 218, WOH G64, UY Scuti, and VY Canis Majoris belong in the conversation. But the conversation is conditional because the measurements are conditional. A fake ending would select one name and let the music swell. A stronger ending returns to the evidence ladder. What definition of biggest is being used? What boundary is counted as the edge? Is the radius direct or inferred? How secure is the distance? How much dust lies in the way? Is the star variable? Could a different temperature scale move the result? Those questions are the real conclusion. So the biggest star is not only an object at the top of a list, it is a problem at the edge of observation. It asks how far a star's atmosphere extends, how light escapes, how distance is known, how dust is corrected, and how much confidence a number can carry. That is a better ending than a crown because it leaves the universe larger, stranger, and more honestly measured. The honest answer is conditional. If biggest means largest estimated radius among known relatively stable stars, then the leading conversation belongs to extreme evolved red supergiants and related candidates. Stephenson 218, WOH G64, UY Scuti, VY Canis Majoris, and other objects may appear depending on the source, method, and confidence threshold. The answer should not be a refusal, it should be a map. Some candidates are famous because older estimates spread widely. Some are compelling because newer modeling places them at extreme radii. Some are valuable because they are better measured. These categories overlap, but they are not identical. A permanent crown would give the cleanest emotional ending and the weakest scientific one. The better ending states the rule. The largest star claim is only as strong as its definition of size, its chosen boundary, its distance estimate, its treatment of dust, and its handling of variability. Change those pieces, and the ranking can change. That leaves the universe larger rather than smaller. The greatest stars are not just giant red balls. They are unstable atmospheres at the limit of measurement, glowing across enormous distances while challenging the language used to describe their edges. The mystery is not who gets the trophy forever. The mystery is how a star can be so large that even defining its border becomes part of the science. The final answer is strongest when it keeps the hierarchy clear. There are famous candidates, extreme candidates, well-studied teaching examples, and possible record holders under particular assumptions. Those groups overlap, but none should be casually treated as identical. A famous name is not automatically the best measured. An extreme estimate is not automatically the most secure. If a name must be offered, it should arrive with conditions attached. Stephenson 218 and WOH G64 can be discussed as leading or extreme candidates depending on the adopted evidence, while UY Scuti and VY Canis Majoris remain important parts of the historical and physical story. The honest answer is not a refusal to choose. It is a refusal to pretend that the choice is independent of method. That is why no permanent crown is the more durable conclusion. The largest known star may change as distances improve, dust corrections sharpen, atmospheric models evolve, and new candidates are characterized. The universe does not become less impressive because the answer updates. It becomes more impressive because the measurement is difficult enough to keep improving. The most useful final answer is layered. By radius, the largest known stars are extreme cool evolved giants, especially red supergiants and hypergiant candidates. Within that group, different names rise depending on the source and assumptions. Any single champion must be treated as provisional, unless the measurement basis is unusually secure. The conditional answer also leaves room for discovery. The sky still contains obscured evolved stars, uncertain distances, changing atmospheres, and candidates waiting for better characterization. Future instruments may refine current names or reveal new ones. A living answer is more honest than a frozen trophy, and it better matches the way astronomy actually advances. The strongest closing answer is therefore not a shrug. It is a disciplined statement. The largest known stars by radius are extreme evolved cool supergiants and hypergiant candidates, with the leading names depending on measurement assumptions and confidence standards. That answer is less tidy than a trophy, but it is more durable. It can accept better data tomorrow without pretending that today's uncertainty was a mistake. The closing thought is simple. The universe does not owe us a stable leaderboard. It offers objects, light, motion, dust, distance, and time. Humans build categories so those objects can be compared. The best answer honors both sides, the real immensity of the stars and the human discipline required to say carefully how large they are. The final discipline is to leave room for better evidence without weakening the present answer. A current leading candidate can be named as a candidate, a former leader can remain important, and a teaching example can remain essential even without owning the record. That layered approach is not evasive. It matches the actual structure of the problem, where size, confidence, and usefulness are related but not identical. That is the standard the answer should keep. Named stars, visible scale, and every necessary condition carried together until the end. The crown stays provisional because the evidence keeps getting sharper over future measurements. So, the biggest star in the universe is not best understood as a single trophy waiting at the top of a chart. If we define biggest as estimated radius, the leading candidates are extreme red supergiants and hypergiants, but the answer depends on the assumptions underneath the measurement: distance, temperature, dust, variability, atmosphere, and the photosphere we decide to count. That is not a weaker ending, it is a more honest one. The universe does not become smaller because the record is conditional. It becomes stranger still. A star can be so large that a solar system graphic struggles to contain it, and still have no hard edge where the question can stop. The biggest star question begins with awe, but it ends with measurement. Somewhere in that fading red atmosphere, light finally escapes, gas becomes space, and a simple question turns into one of the most beautiful problems in astronomy. Not just how large can a star become, but where does a star end